Hello my dear students, welcome to our channel Mallesham Creations. Today's topic is Molecular Orbital Theory, MOT. Before going into Molecular Orbital Theory, if you did not subscribe our channel, please do subscribe. Now we will see what is Molecular Orbital Theory, what it explains, who proposed this theory, everything in detail. This MOT theory explains the structure and properties of different diatomic molecules. For example, for diatomic molecules is N2O2 F2. These are examples for diatomic molecules. N2 is a nitrogen molecule. It is a combination of two nitrogen atoms. O2 is a oxygen molecule. It is a combination of two oxygen atoms, etc. We will see what kind of atomic orbitals will overlap everything in detail. This theory was proposed by F. Hund and R.S. Mulliken. Hund and Mulliken proposed this theory. So what kind of postulates are there in this theory means what kind of atomic orbitals will combine each other to form molecular orbital. Then what kind of molecular orbitals are formed, or they having same energy, or what kind of bond order, magnetic property, everything we'll see in detail. So first compulsory property in this one is only atomic orbitals having similar energy and proper symmetry only combine each other to form molecular orbital. This is the first criteria. The atomic orbitals which are going to combine, they should have similar energy and proper symmetry. Then only those two atomic orbitals will combine each other to form molecular orbitals. Next, the second question is molecular orbitals are forming, but how many they will be formed? That is, total number of molecular orbitals formed is equal to total number of atomic orbitals combined. That means there is no wastage of atomic orbital. For example, 10 atomic orbitals are combining each other, 10 molecular orbitals can be expected. The third question is, all the molecular orbitals are same? Answer is no. If n number of atomic orbitals are combining and forming n number of molecular orbitals, out of n molecular orbitals, n by 2 are bonding molecular orbitals, and another n by 2 are called as anti-bonding molecular orbitals. Because bonding molecular orbitals are formed through in phase, anti-bonding molecular orbitals are formed through out of phase. What is bonding molecular orbital? Molecular orbitals which have lower energy than the corresponding atomic orbitals is called as bonding molecular orbitals. Bonding molecular orbitals are formed through addition method or constructive interference. Next, and what is antibonding molecular orbital means? The molecular orbitals which are having higher energy compared to the corresponding atomic orbitals is called as antibonding molecular orbitals. Antibonding molecular orbitals are formed through subtraction method or destructive interference. So up to this point, we will come to know that what kind of atomic orbitals are forming and what kind of molecular orbitals are forming. Okay, after formation of molecular orbital, we should fill molecular orbitals with electrons. How to fill molecular orbital? Similar to atomic orbitals, following above Wund's and Pauli's exclusion principle. Molecular orbitals can be filled with electrons following three rules, that is Above rule, Wund rule, and Pauli's exclusion principle. So up to this point, formation of molecular orbitals and filling of electrons is over. Then we should get the properties of the molecule. What kind of properties? That is the bond order. Bond order is equal to Nb minus Na by 2. Nb stands for total number of electrons present in bonding molecular orbitals. Na stands for total number of electrons present in antibonding molecular orbital. Next, the eighth point is bond order. What we measured here should be positive. Then only that molecule is stable and exists. If the bond order is equal to 0, that molecule is unstable, that means molecule does not exist. Therefore, it is crystal clear that molecule should have positive bond order, then only that molecule exists. If bond order is equal to 0, molecule does not exist. Another important property of the molecule is magnetic property. If molecule possesses one or more unpaired electrons in its molecular orbitals, then that molecule will have paramagnetic property. If molecule is having unpaired or lone pair of electron, that molecule will have paramagnetic property. If molecule does not have any unpaired electrons or lone pair of electrons, that means all the molecules present in the molecular orbitals are paired. That molecule will have diamagnetic property. It is clear that what kind of atomic orbitals are combining and how to calculate bond order and magnetic property using MOT theory. Thank you. Applications of molecular orbital theory. The first application is construction of molecular orbital energy level diagram of nitrogen molecule. We will see how nitrogen molecule is formed, what are the properties of nitrogen molecule. As we know that atomic number of nitrogen atom is 7, number of electrons present in nitrogen atom is 7. Therefore, number of electrons present in nitrogen molecule is 14. The electronic configuration of nitrogen atom is 1s2, 2s2, 2p3. We will see how nitrogen molecule is forming. To form nitrogen molecule, the atomic orbitals present in nitrogen atom should overlap each other. We know that the atomic orbitals present in nitrogen atom is 1s2, 2s2, 2p3. Similarly, in another nitrogen atom also 1s2, 2s2, 2p3. All these atomic orbitals should overlap to form nitrogen molecule. So MOT theory explains that the first criteria in MOT theory is that to overlap atomic orbitals, they should have similar energy and proper symmetry. In that case, 1s atomic orbital and another 1s atomic orbital will fulfill this criteria. Therefore, 1s atomic orbital of one nitrogen atom, another one and one more 1s orbital of another nitrogen atom can overlap each other because those two only will have similar energy and proper symmetry. Therefore, at the similarly, 2s atomic orbitals of one nitrogen atom can overlap with 2s atomic orbitals of another nitrogen atom. Similarly, 2p atomic orbitals of one nitrogen atom can overlap with 2p atomic orbitals of another nitrogen atoms. So now we will see, this is the energy order. From bottom to top, energy is gradually increasing. Now we will see the molecular orbitals resulting from the overlap of atomic orbitals. These are the molecular orbitals, resulting molecular orbitals after overlapping of atomic orbitals. The name should be given to the molecular orbitals. How to give name? That means atomic orbitals are represented by S, P, D and F. However, the molecular orbitals can be represented by sigma, pi, delta, etc. In molecular orbitals, as we discussed, there are two types, bonding molecular orbitals and anti-bonding molecular orbitals. Bonding molecular orbitals can be represented by sigma, pi, delta. However, the corresponding anti-bonding molecular orbitals are represented by star symbol. Now we will see. This is the sigma 1s molecular orbital. Why only sigma 1s atomic molecular orbital? Because 1s after overlapping of 1s can give only sigma type molecular orbitals. That will be explained in another video. So 1s overlaps can provide only sigma. This sigma molecular orbital is resulting from 1s. Therefore, the name given for this molecular orbital is sigma 1s. As we know that this is the anti-bonding molecular orbital. When bonding molecular orbital name is sigma 1s, automatically the anti-bonding molecular orbital name is sigma star 1s. Similarly, this is the sigma star 1s. Similarly, 2s atomic orbital can overlap with another 2s atomic orbital. The resulting molecular orbital name is sigma 2s. Because 2s atomic orbital overlapping with 2s atomic orbital can provide only sigma molecular orbitals. This sigma molecular orbital is resulting from 2s atomic orbitals. Therefore, this name is sigma 2s. When the bonding molecular orbital, this is the bonding molecular orbital. When the bonding molecular orbital name is sigma 2s, automatically the anti-bonding molecular orbital name is sigma star 2s. So here, this is the major difference between less than or equal to 14 electron and greater than or equal to 14 electron. We will see now. So the 2px and 2py atomic orbitals of one nitrogen atom and 2px 2py atomic orbitals of another nitrogen atom can provide pi 2px and pi 2py molecular orbitals. Pi 2px and pi 2py molecular orbitals have same energy. These two molecular orbitals are also known as degenerate molecular orbitals since they have similar energy. After that, 2pz can overlap with another 2pz. Atomic orbitals can provide sigma molecular orbital. Therefore, that name can be given as sigma 2pz. This is the major difference between nitrogen atom molecules having less than or equal to 14 electrons like nitrogen molecule and molecules having greater than 14 electrons. Here, this is the major difference. In the molecules having less than or equal to 14 electrons will have pi 2px and pi 2py is lower energy, pi 2pz, sigma 2pz. Determine the magnetic property of this molecule. Since nitrogen molecule doesn't have any unpaired electrons, it will have diamagnetic property. If it is having unpaired electrons, it is paramagnetic. Since nitrogen molecule doesn't have any unpaired electrons, its magnetic property is diamagnetic in nature. Next, we will see the molecular orbital energy level diagram of oxygen molecule. Similar to nitrogen atom, the electronic configuration, the atomic number of oxygen atom is 8. Therefore, number of electrons present in oxygen atom is equal to 8. Number of electrons present in O2 molecule is 16, just double. Electronic configuration of oxygen atom is, we know that 1s2, 2s2, 2p4. Similar to nitrogen atom, here also oxygen atom is having 1s2, 2s2, 2p4 atomic orbitals. Another oxygen atom is having 1s2, 2s2, 2p4 atomic orbitals. The energy order of these atomic orbitals is gradually increasing from bottom to top. So how atomic orbitals of one oxygen atom overlap with another oxygen atom to form molecular orbitals is given here. So as mentioned by MOT theory, 1s atomic orbital can overlap with another 1s atomic orbital due to energy and symmetry criteria, can lead to formation of two molecular orbitals. Out of two molecular orbitals, one is bonding molecular orbitals. That name can be given as sigma 1s. Since s orbital overlapping with another s orbital can lead to formation of only sigma bond. Therefore, the name given for this bonding molecular orbital is sigma 1s. Automatically, the corresponding antibonding molecular orbital name should be given as sigma star 1s. After this, 2s atomic orbital can overlap with another 2s atomic orbital can lead to formation of sigma 2s, and automatically the antibonding molecular orbital name can be given as sigma star 2s. 2pz atomic orbital can overlap with 2pz atomic orbital of another oxygen atom can lead to formation of sigma molecular orbital due to symmetry criteria. Therefore, the formation of sigma 2pz molecular orbital. After this, 2px and 2py atomic orbitals can overlap with 2px and 2py atomic orbitals of another oxygen atom can lead to formation of pi 2px and pi 2py molecular orbitals. Both molecular orbitals have same energy. Similarly, the antibonding molecular orbitals names can be given as pi star 2px and pi star 2py, sigma star 2pz. Molecular orbitals, electrons should be filled into molecular orbitals. Here, 1s atomic orbital and 1s atomic orbital both are having 4 electrons altogether. Out of 4, 2 electrons are filled into sigma 1s molecular orbital. The remaining 2 electrons are filled into sigma star 1s. Here, 4 electrons are there in 2s atomic orbitals. Therefore, 2 electrons are filled into sigma 2s molecular orbital. Remaining 2 electrons are filled into sigma star 2s molecular orbital. Here, total 8 electrons are there in 2p atomic orbitals. Out of 8, 2 electrons, according to Aubert and Pauli's exclusion principle, first 2 electrons are filled into sigma 2pz. After that, 1 electron is filled into pi 2px and pi 2py, and next pair up takes place. That means 2 electrons are filled into pi 2px and pi 2py molecular orbital. However, here it is clear that still 2 electrons are left over. Therefore, 1 electrons coming and filling into pi star 2px and pi star 2py molecular orbitals. Here the major difference between the nitrogen atom and nitrogen molecule and oxygen molecule, you should remember that sigma 2pz molecular orbital is having lower energy compared to the pi 2px and pi 2py. This is the main difference. Many students are confusing here. You should remember that's one. The difference between nitrogen molecule and oxygen molecule. Like this, molecular orbitals are formed and molecular orbitals are filled with electrons. This is called as bonding molecular orbital since these molecular orbitals are having lower energy than the corresponding atomic orbitals. These molecular orbitals are known as anti-bonding molecular orbitals since they have higher energy than the corresponding atomic orbitals. Here also same. This is ABMO, this is BMO, this is ABMO, this is BMO. After construction of molecular orbital energy level diagram, MOED, we can write electronic configuration of O2 molecule is from bottom to top we should write, because since energy is increasing from bottom to top, therefore first initially we should start from here. This is sigma 1s molecular orbital. This is having two electrons, therefore the electronic configuration sigma 1s2. After this, higher energy is there for sigma star 1s, therefore after this sigma star 1s2. Next energy level is sigma 2s. This is having two electrons, sigma 2s2. Next sigma star 2s2. After that sigma 2p z2. Next pi 2px and pi 2py have two electrons, therefore pi 2px2, pi 2py2 both are having same energy, therefore that should be right in the brackets. After this, pi star 2px and pi star 2py molecular orbitals are having only one electron. Therefore, this is the electronic configuration of O2 molecule sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2 since both molecular orbitals having same energy. After that, pi 2px1 is equal to pi 2py1. This is the electronic configuration for O2 molecule. Next, we should determine the bond order. Bond order is equal to Nb minus Na by 2. Nb is total number of electrons present in the molecular orbitals. Here, in bonding molecular orbitals, 2, 4, 6, 8, and 10. 10 electrons are there in bonding molecular orbitals, therefore 10 minus the total number of electrons present in anti-bonding molecular orbitals is 2, 4, 5, and 6. Therefore, 10 minus 6 by 2 is equal to 2. Therefore, it is confirming that the bond order in O2 molecule is 2. That means O double bond O. The double bond is present in between two oxygen atoms. After this, we can determine the magnetic property for the molecule according to MOT theory. Here, we can see that unpaired electrons are there. Two unpaired electrons are there, or two lone pair of electrons are there. Therefore, O2 molecule is having paramagnetic property. Like this, we can determine bond order and magnetic property of any given molecule using MOT theory. MOED of another molecule, that is fluorine. The atomic number of fluorine atom is 9. Therefore, the number of electrons present in fluorine atom is 9. Immediately, the number of electrons present in fluorine molecule will be 18. The electronic configuration of fluorine atom is 1s2, 2s2, 2p, 5. Similar to N2 and O2, here the atomic orbitals for fluorine atom is given, that is 1s2, 2s2, 2p, 5 for one fluorine atom and 1s2, 2s2, 2p, 5 for another fluorine atom. The energy order is increasing from bottom to top. According to MOT, the atomic orbitals will be overlapped by fulfilling the 10 points. Therefore, here the resulting molecular orbitals are shown. 1s atomic orbital can overlap with 1s atomic orbital of another fluorine atom, can lead to the formation of two molecular orbitals. Out of two, one is bonding molecular orbital, another one is anti-bonding molecular orbitals. The names should be given for these molecular orbitals following rules that this molecular orbital is sigma 1s because 1s formation can lead to sigma bonding. Therefore, this molecular orbital name is sigma 1s. Automatically, this molecular orbital name will be sigma star 1s. This is anti-bonding molecular orbital. After that, this is sigma 2s. This is sigma star 2s. Next, in the case of fluorine, since it is having greater than 14 electrons, at first 2pz and 2pz can overlap takes place and formation of sigma 2pz. After that, pi 2px and 2py atomic orbitals of two oxygen atom can overlap with each other and leads to the formation of pi 2px and pi 2py. Next, antibonding molecular orbitals names will be given. Pi star 2px is equal to pi star 2py and another one is sigma star 2pz. After formation of After formation of molecular orbitals, the electrons should be filled into the molecular orbitals following three rules above Hund and Pauli's principle. Therefore, according to those rules, sigma 1s atomic orbitals are having 4 electrons. Out of 4, 2 electrons are filled into sigma 1s. The leftover 2 electrons will be filled into sigma star 1s. Similarly, sigma 2s, sigma star 2s. After that, in the case of 2p atomic orbitals, total 10 electrons are there. Out of 10 electrons, first 2 electrons are filled into sigma 2pz. Next two electrons, at first one electron is filled into pi 2px and pi 2py. Next another one electron will come and pair up with the initial electrons. Therefore pi 2px, pi 2py will be filled into two electrons. Still we can see here that two electrons. That means still 4 electrons are available in atomic orbitals. Those 4 electrons will come and fill into pi star 2px and pi star 2py following above Hund and Pauli's principle. At first one electron and next one more electron will come and join with the first electron. Therefore, like this, molecular orbitals are formed and electrons are filled into molecular orbitals. This is called as bonding molecular orbital. These are called as anti-bonding molecular orbitals. Since these molecular orbitals having lower energy than the atomic orbitals, these molecular orbitals are having higher energy than the atomic orbitals. Therefore, they are called as anti-bonding molecular orbitals. Like this, we can construct MOED diagram for fluorine molecule using MOT theory. After this, we can